It's time for us to all these inspiring talks for the future. We'll have a Nobel laureate firms, we'll have president of academic firms, we'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future.
Hi, everyone. Welcome to iCANX Talks. I'm Len Fu, a professor in physics from the Australian National University. Tonight, we have our 182 iCANX Talks. And this talk, we have a special speaker, Professor Xinge Yu from City University of Hong Kong. We also have a special panelists joining us tonight for a special edition in celebration of the 4th anniversary of iCANX Talks. So at first, let me introduce you our speaker tonight, Professor Xinge Yu from City University of Hong Kong. Xinge is associate professor of biomedical engineering at City University of Hong Kong, member of the Hong Kong Young Academy of Sciences, associate director of the Hong Kong Center for Cerebral Cardiovascular Health Engineering, and associate director of the City Yu Joint Lab on Robotics. Dr. Yu is the recipient of RGC Research Fellow Innovators Under 35 China and an NSFC Excellent Young Scientist grant, as well as New Innovator for IEEE NanoMed, MINE Young Scientist Award Gold Medal in the Inventions of Geneva, and CTU Outstanding Research Awards, Stanford's top 2% most highly cited scientists, etc. Xinge's research group is focusing on skin-integrated electronics and systems for VR and biomedical applications. He is the associate editor and editor board of over 10 journals, as well as he has published 160 papers in Nature and a series of Nature sister journals. And also he has 40 patents and files granted. So with that, Professor Xinge Yu, the stage is yours.
Okay, let me share the screen.
Yep.
Okay, thank you, Professor, for the host for the kind introduction. And also thank Professor Alice Zhang and iCANX to give me this opportunity and a great platform to talk about our works. So this is actually my second time talk on iCANX. And this afternoon, I just go back to see what's the contents I talked in the last time, which is in 2020. And so I can guarantee, it's over 90% of the contents I'm going to talk about today is brand new, okay? Hello, everyone. My name is Xinge Yu from City University of Hong Kong, the Department of Biomedical Engineering. And today I'm very, very glad and honored to share with you our recent work, the intelligent soft electronics for healthcare monitoring and virtual reality applications. Okay. So we started from the evolution of electronics. So from this timeline, we can see in the past 70 years, so also 100 years. So the human has made a big progress in the development of electronics. So from the different formats to the different functions. Well, in the very early stage, so our electronic devices are basically based on the vacuum-based like a diodes and trials and something, and then converted, developed into a new technology with integrated circuits as well as the solid-state electronics. So this is a very big milestone for the future development of the topic I'm going to talk about today. I mean, the soft electronics. And until the discovery of the conductive polymer, people realized electronics can be in another format rather than these bulky or these vacuum things, right? And so we can compare to the differences. So like almost 80 years ago. So in 1946, so people started to build this computer called the ENIAC, electronic numerical integrator and computer. So after almost 10 years, right? So people built this one, and the whole system occupied this over 160 meters square, and so weighs many tens of tons, and so power consumption is also huge. But the function of such electronics is so it's quite limited. Well, we can compare to the 2020s technology. So that's a bendy smartphones. I guess quite a lot of people are using this type of cell phones. This is a big change of electronics formats. People realize electronics can not only be in these rigid formats, can be also in the soft formats. And I think this is also the very beginning where electronics started to be flexible, that flexible display. Well, the electronics in flexible formats is more than that, right? So here I listed some flexible electronics. I would say the soft electronics, right, and their applications. So from the very recent hot topics, the humanoid robots, right? So people try to build this type of robots. I think it's rather than the needs, right? So it's also based on the people's imagination, especially for me. When I was a kid, so when I read any news about the robots, I feel this robot is like a human. This is not. And in my mind, I only thought that this robot looks like a human. It's a real robot, right? It's a real robot. Well, if we can develop soft electronics and to give the robots some sensing capability, so in a skin format, so which can mount on the surface of the robot's body, it can be electronic skin, right? So it's called robotic artificial skin. So which is a huge application area and potential for soft electronics. And the second area I'm also going to talk about today, that is the prosthetic sensing and control. So it's another kind of a human-machine interaction. And the user can use these soft electronics as a manipulator, right? Assign a command to the machine or the prosthesis. So, and then to grab it to doing some tasks and grabbing something, right? Well, at the meantime, so you will find some new opportunities in this area. We call it the haptic interface. I'm going to talk about today also. And another application area is the wearable or even implantable devices. So if we want to wire the electronics on our body, so everyone knows in these fields, we can monitor these physiological signals, biosignals, or the chemical signals, right? So from different perspective views, it has to be flexible, right? It has to be integrated with the human body. The reason is, so if there's like a gap and the not perfect contact, so between the devices and the human body, so the sensing signal may not accurate, right? And so when we try to use such electronics so with the application for the implantable purpose, it's also need to be flexible. The reason is our organ, I mean, especially the inner organ, is very, very soft. And only the electronics with this small miniaturized feature as well as the very soft feature, it can conformally mounted or integrated with the tissue and for this purpose we use, right? And the last application, not least, right? So I mean, it's the list in these slides, but I think it's more than that. So that's attracted me a lot. So an opportunity for soft electronics, I think. So I feel it's the gaming and entertainment, right? So especially for the VR game. So probably some people already play the VR game, also watch some movie or the TV shows that people use the advanced instruments doing the entertainment or even training or something. And in this case, think about these gloves can track the motion, right? There's a shoes can give you some additional experience rather than sensing, but also the feedback. That's all based on the technology of the soft electronics, right? It needs to be bendable or even stretchable. Well, based on these demands and areas, so today, so this is the contents I'm going to share. That is the research areas our group has been working on, and you can find these representative works. So we published. And our group are working on these four areas. The first one is the skin integrated or wearable formats for the virtual reality application. So augmented reality application or the mixture or extended, so we call it XR, right, applications. And talking about VR, so you can just simply, right, so think the virtual or environmental, so the objects to be a robots, and how do user interact with the robots? So that is a concept of human-machine interface, right? So what is the interface? The soft electronics. We use the soft electronics as an interface to either control the machine or to receive the information from the machine, right? So this is our second research area. And our third research area is basically, which is for the purpose of the fourth area. So the skin electronics, I would say, is more focused on the soft and functional materials. And we try to develop some new devices and materials to solve these very, very fundamental and so these technical bottlenecks for the wearable and soft electronics, such as the interfacial property, right? So air permeability, long-term stability, so the sensing accuracy issue, right? And so this works. So since so I have materials background, but I'm not expert in this area, and so we do a lot of collaborations with many great colleagues, right? And the last research area I'm going to share about today, so is the biomedical applications. So we find the very so the urgent, right? So needs, so from the clinical side, so such as these physiological signal monitoring and disease diagnostics and these areas, and what's the gap between engineering and the medicine, and we build a bridge to bring this area together. So that's a biomedical application, right? Okay. Now let's start it from the first one. And so this is a kind of a new concept, but I think it is a very good start point, right? So by starting this topic, so I would like to share this videos as I always share this video for my presentation. So this movie trailer called, this movie is Ready Player One. There's another very fancy name for such content called metaverse, right? So in this movie, you can find in the virtual reality VR environment, so human can interact with the virtual character, not only in the game, but also with other users, because there's a metaverse, right? The platform, such as the iCANX, so bring everyone here. And the only difference now, you can see me, so I can also see you, but you cannot touch me, right? Well, the difference in this Ready Player One or the metaverse, the people can not only see each other, hear each other, most importantly, they can also touch each other, right? People can feel the touch. How to realize that? Based on these suits, right? Based on these wearable electronics, right? Wearable devices. Well, from the movie, so we can find, so these wearable devices, there's a name called a haptic interface, right? Haptic interfaces exist everywhere, so such as your cell phone, when it's vibrating, sending the message to you, so this can be also a haptic interface. The joystick, you are playing the video game, so there's a feedback when you kick something, right, punching something, that's also the haptic feedback interface. Well, if we want to realize the Ready Player One scenarios and this application, what is the haptic interface need to be, right? In the virtual world, when other people tap you and you feel someone is tapping you, that's here, so the haptic interface need to be wearable, very thin, soft. And another thing, it cannot be held by your hands. Otherwise, you cannot release your hand, right? It need to be passive, so other people touch you like the real world. Another thing, for such a haptic interface, so when some people touch you or you have interactions such as a shaking hands, what you can feel, several informations. You can feel the force. You can also feel the temperature, and you can also feel the fine texture, such as if you're shaking hands with a very strong, so men, so who all doing the sports, so like a bodybuilding, you feel this very strict hands, right? And also, so maybe it's a very warm and also the very rough surface of the hand. So that's all the feeling you can feel. And we want this haptic interface to provide as many as this tactile information to the user and realize this very immersive experience for the VR environment, right? So, and the story started here, but we need to start step by step. And this story begins as early in 2017. So at that time, so I was a postdoc in Professor John Rogers' group, and we initiated the idea. And the time we initiated the idea, we realized, oh, this is really interesting. Since most people at that time, so they working on flexible electronics, mainly focus on sensing capabilities. Very few people think about can bring the force feedback to the users in a wearable format. In this case, so we try to develop some like wearable electronics with very thin formats, can be skin integrated and mounting on the body, can provide this programmable feedback with these 32 mechanical actuators array, right? So each actuator can be activated individually. And as I mentioned, this was the start work. So the purpose to show the idea. So we need to find the most efficient way to bring this actuator in a very thin, soft, and a miniaturized format. And we decided to use the electromagnetic driven method based on Lorentz force. And we can find there is a copper coil, right? And also a supporting ring based on silicon and polyimide polymer, so membrane as a handle to hold a permanent magnet. And when you input the AC electricity, alternative electricity into the copper coil, and it will generate exactly the same frequency the signal you input. And so this magnetic field around this copper coil will make the magnet vibrate. And when your body contact with the magnet, you feel the vibration, right? And so the task is very simple for us. It's to make this actuator very high efficiency as well as small as possible. And we use the mechanical resonance design format, which is collaborated with Professor Yonggang Huang and also my collaborator, so Professor Zhao Jianxie. Now it's in Dalian University of Technology. And we make such a device is very thin, soft. And so also there's we need to notice the human most sensitive frequency. So I would say it's around 200 hertz. And you can try that. And make all these actuators in an array, and also including how to cancel the mechanical interferences. And we can have these larger array electronics with the well-established stretchable electrical so circuits and components so in the device, and so make it stretchable and bendable. The application of such devices can be in many areas, such as the gaming I already mentioned. When you play a video game, the punching game, right? So the fighting game, so you control the character, no matter the punch or being punched, the particular part of your body, so that's associated with the gaming character, will give you the very immersive feedback. You feel just doing the fight by yourself, right? Another application area that is very similar to the concept just mentioned, right? So now we can see each other. How about we can touch each other virtually? And here we use the example is a case doing a video chat with the family member. And we put this skin interface, the VR system, right? We call it skin VR on the body of the case. And the family member can touch the screen. And this touch information can wirelessly transmit the sound command to the haptic interface, bring this different pattern vibration force, and the user can feel that, and which bring the haptic, so I mean the tactile, from the real world into the virtual world. Okay. Another application, so it's also very important, that is more related to biomedical engineering. That is a prosthetic sensing and control. And because according to the WHO, there are quite a lot of people. So due to the different, so it can be accident, or it can be disease such as diabetes. So they have to do this surgical procedure, right? So and the amputee, so surgical procedure, and so next, so they can use like a prosthesis to replace so the arms or legs. And so typically people use the EMGs, the muscle signal, as the command to control the movement of the robotic hands. However, so even the robotic hand can grab something, right? But the user cannot feel that. And the reason is, so there's no connection, the interface between so the device and the brain. And what we do that is we can put the skin VR at the end of the amputee arm, and which is a coordinate with the sensors on the robotic hand. When the robotic hand is sensing this information, and it can wirelessly transmit and send a command to the feedback system, can give you the particular feedback, and the user can feel that, and he can think and feel just like he are using his own or her own robotic hand to grab these things. Okay. And here this video shows how the user used this one to control the robotic hand doing the grab, such as he used the hand to grab this one and he can feel the force. No need to push it very hard, right? To better control the force. Okay. And the story is started, and then we seek the further opportunity, and it's very, very interesting. So in 2020, 2021, the Meta, right, the former Facebook, so that's announced that they are doing the metaverse, right, doing the metaverse. It's based on the VR glasses, the virtual contact. And they also realize how to bring this haptic interface into the metaverse is very, very important. It brings the metaverse into another level. Well, the Meta so gave the design, so strategies using these air bubbles, right, pneumatic things, right, so to pumping and depumping these small real or air bubbles on the glove, and people can use the force, right. So I think there's quite a lot of advantages with such technology, such as the force is bigger, right, so can be static force and so also programmable, but there are also some technical challenges need to be solved, such as the external instrument to, for gas supply, as well as a time delay, and also there's still a lot of room to make such a system to be thin and soft, or even so in a portable format, right? And so this work is newly online, which is led by Professor Zhengbao Yang. So we collaborate with Professor Yang's group, and we use the pneumatic method to bring the multiple skill habitat interface by pumping and depumping these small air bubbles, and then can create these different tactile sensation. And we can find from the fingertip to the arm as well as the back, and by using this one, can do this a lot of work. Well, at the same time, we were thinking, so how to use this technology with this idea with another technology. And especially, so the habitat interface can be very, very thin and small, right? So since you use the air bubble method, so it's very, very hard to decrease the dimension of the device into like a thin, soft format, like the traditional flexible electronics or skin electronics formats thinking about, right? So electrotactile so just came to our mind. So we know this is very, very good technology, can also reproduce the habitat sensation when you put a electrode contact with our body. Why it's not widely used in the habitat interface, and the reasons limitation in the dimension flexibility. And if you have ever used or your family member used this electrical stimulation instrument, you can find it's quite bulky due to the power density and a lot of issue. Another thing, I think this is most critical, that is that people are so different among each others, right? So if you use the same number of the current input, right, into the different people, I mean, same value of the current into the different people, people may have different sensation. Some people with the degraded, such as mechanoreceptors, they feel nothing, and some people may feel this painful. And this limitation that makes such like an electrotactile technology is very, very hard as a universal technology to adapt to everyone, right? So that's the reason. I think to solve these two problems, it's a good start for this habitat interface based on electrotactile. And here's our solution. And we use this one to start and develop this thin, soft, wearable habitat interface with the wirelessly feature as well as very thin, soft. Most important thing is a universal method to all the people. How we do that? So we separate into the two-step, decoding and encoding. And then we can realize such system to interface with VR environment, as well as to provide this very immersive sensation of the habitat feedback just by electrical stimulation, right? Without anything else, right? So here is a device. So formats we can find. So it's very thin, soft. I think it is the most, so the smallest devices in the world. Right? So that's based on the electrical tactile. And so the purely based on the, so adjust the modulation of the input electricity and the duration and amplitude of the electrical signal. And so the device contains two parts. The first part is the driving circuits part. So we use the like a flexible print board, FPCB, and these are MCU and also electronic components, which is powered by a small battery and of course rechargeable. And if you want to use electrical stimulation, you have to use the reference electrode. And this reference electrode, so here we make the reference electrode as the based on the hydrogel electrode, which is the big area, so the current density will be very low. Then you just feel the electrical stimulation on the stimulate electrode, so which is on the other hand, right, the skin patch. And the skin patch, so we use the materials, the well established the stretchable concept of the metallic serpentine lines. And so this is the dry electrode. To make the adhesions to be very good with the skin, we also use the conductive hydrogel on the electrode surface. The other area we encapsulate that. And on 2 points, so on the first hand, on one hand, so the whole patch is very, very sticky on our hand. It's without the delamination will even move. And on the other hand, so it can maintain good stretchability for this interconnect because we use the mechanical design for such a electrode. And so how we control such a device, we purely use electricity, right? And we can use a different loading resistor to control the input voltage. Since if we want to use electrical stimulation, you need to have a very, very large voltage to create such a large electrical field. And the current can be small, right? But the voltage needs to be high. So the voltage can be controlled from like a tens of volt to over hundreds of volts. And you also need to control the duty cycle, right? The duty cycle that's give the sensation of the strong or not, as well as the frequency, right? The current can be also controlled by input different power density. By controlling the frequency, the voltage, and the duty cycle, the current, and we can give so many information to the Happy-Tech interface. And next thing is the most important thing, as I mentioned, we do the decoding, right? Tactile decoding for these whole patch so devices, right? So we separated, so we divided into different level from this weak, right? You feel very, very weak. So no feeling, you feel nothing. And it's very, very weak, such as some people use the fur, right? So it's a leather. So it's that's tickling on your hand. Also, the gentle touch, you touch something very gentle, or it's appropriate, or slightly uncomfortable, or it's these are painful, right? Uncomfortable. So most of the time, we prefer the sensation is falling into the appropriate region because people feel this so appropriate feedback. And we do a lot of study, the user study based on the different genders, different ages. And for the purpose of to decode the tactile information over the hands of each individual, right? So here, so we give the solution is we decode the tactile information on each individual person. And based on the decoding information, we encode into these electrical electrodes, and so it can be universal to everyone, right? And from the results we can find, so either the frequency and the current density will give us a different sensation. And on different parts of our hand, you need to use a different frequency and different amplitude of the current to give you the appropriate sensation, right? That's all the data shown here. With all this information, that's we encode this tactile information on our hand. And first, we do the demonstration with AR. Firstly, we ask the student to hold a real tennis ball, and we test the pressure distribution on our hand. With this pressure distribution information, we input the electricity of the Happy-Tech interface to the different points, which to mimic the AR-generated tennis ball. We are holding an AR-generated tennis ball shown here. and which is the current shown here, you really feel something is in your hand, right? So you really feel something in your hand. And next, we do the dynamic demonstration. That's we develop a very like a simple game that is a small mouse running on your hand to steal these cheeses, right? So when it's moving around, so each point you can feel the tickle feeling, right? So that's all. But the current density is differences when the people feels the very uniform, right, sensation. And based on these results, we can also use such technology to embed it into the VR environment. Well, in the VR environment, it's very interesting. So exactly the same, but you just build like a 3D environment. You can not only touch a tennis ball, but you can also touch something else, such as the like a cactus. So which is also ball, but it's the very like a sharp, right? So it's when you touch it, you feel the painful thing, right? And I mentioned if we change this virtual object into robots, that's a human machine interface. And at that time, so we gave some idea to show the human machine interface based on both sensing and feedback, right? Like shown in these two videos, right? Well, so next, so I will detailedly talk about this human machine interface based on this technology, right? Well, this work I just mentioned is based on the electrical tactile. However, electrotactile gave us the sensations very limited. The first one, so the earliest one, so that is based on the mechanical stimulation. And so the previous one I mentioned is electrotactile. And so how to give people that's very, very fine texture and immersive feeling, that's we use a multiple mode sensation. Since the mechanoreceptors are under our skin, so that's associated different sensation feelings when we touch objects, including this temperature. That is the reason. So the different materials have different thermal conductivity. Such as if you are holding a glass, you feel the cold, right? Holding a steel is a cold, and if you are holding like a wool, like a cloth, right? That is a wall, right? Because the thermal conductivity between this steel and this yarn are different. And you also feel the roughness, right? You feel the force. And so if we can mimic all the sensation, this can give you this very, very real or immersive feeling. So based on this habitat interface. So we combine the temperature, mechanical, electrical, tactile together to give the different sensation and combine, and then so use algorithm to give the well-defined programmable signals. So the thermal information we use the thermoelectric, inorganic thermoelectric that can not only so heating up, but also cooling down the temperature. Well, for the mechanical stimulation, that's mimic the large force, and also electrical stimulation that give us a fine texture, right? People can feel that. When we combine these things together, that's a very amazing things happen. If you only use these electrical stimulation, you can find it. So in the low frequency, it can do a lot of things, right? Do a lot of things. But high frequency, due to the electrical fields cannot penetrate into the very so in-depth the tissue, we need to use a mechanical stimulation to reach this area. So we just cover all these blank areas and make them together. And at the same time, we use electrical stimulation to mimic the fine texture, because when you use a finger slide on the table or any materials in a very, very small scale, you can just so to like a simplify the surface roughness like a periodic, right? So formats. Well, so when you like slice on these periodic waveforms, so you just input, so these are related frequency, so current frequency, that can just mimic this fine texture. We combine all the things together can give you the very, very good sensation. Most important thing is all these technologies, we need to make it into a soft format. We cannot hold it, right? So all the time. We also want to use it passively, either like a sleeve or it's a band or some things, rather than a glove, right? And we integrated them, and so to study these so user studies, and we found the different materials. So based on the adoption of 3 modes, multiple modes, we can so increase the sensing accuracies significantly. People are feeling that just holding, touching these particular materials. If you use a single mode or 2 modes, so the accuracy is not good, right? It's not good. And then, so we show the application of such technology to use in the VR environment, such as the user so put the skin integrated Hypertext interface, and based on our developed the VR environment, which is collaborated with our colleague Professor Ke Zhu from Creative Media Department of our university, right? They built this very nice 3D environment, and so we can find that the students touch the surface of the table, but it's virtually, but she feel it just touch the real thing. And when she like grab a glass, you can find the temperature is cooling down. And pouring the hot water inside, the temperature increase immediately until it's very hot, right? Just like you are holding a real cup of water, hot water. For the outdoor scenarios, that's when we put this device on the body, when it's the winding, right? So no matter it's heavy or it's a light, strong or light, so you can feel the vibration at your sleeve, which is created by the mechanical actuators so on the band. And when it's raining, the rain droplets so falling down on your hands, you feel this cold feeling, and also something, and a caterpillar also is falling down on your arm, you feel the itchy, right? And so the people just shake it off. Okay, so next, I'm going to share our work, so which is another dimension of the virtual reality. So beyond the visual, beyond the auditory, beyond the tactile, that is the smell, right? Smell, olfactory, right? So here, so a lot of people are working on electronic nose. That's a sensor, gas sensors. Here, difference. Here we input electricity, we release gas, we release smell. How we do that? We also use the foundation of the flexible electronics, but so it's very simple principle. We mix the wax with the perfume, right? So just like a candle you use to help you to go to sleep, right? And when you heat up the phase transition of the candle of the wax, so the smell can be released. So we miniaturize and make the good mechanical design and so the electronic design of such a skin interface, the auto generators, which can be used the olfactory virtual reality system. So from a pile of devices into the 3x3 9 actuators in one, so integrated into a mask. And so by optimizing the performance of the device, so you see the response time and the closing time of the device is very, very good. And which is because we also have the mechanical actuators to holding up and so pulling down, and the temperature can be dissipated very fast. And then people don't feel the time delay. So when we use such device interfaced with the virtual environment, you can see the user can smell this information, right? And purely by control the input electricity intensity, so difference, and people can feel the different intensity of the smell. So such system can used in many areas from the virtual reality and also the 4D movie and also medical training, many other things. So also there's help people to know so other things such as some plants, flowers. So from the VR environment, we can not only see, but we can also smell that, the smell virtual reality. Well, there are so quite a lot of works. I think it's a big opportunity in this area, such as how to improve the response time, how to make the latency free, as well as how to miniaturize the device, use a different principle. I think there's quite a lot also room for this area, right? And so here's the review. So from the physical part, so we're still working. We have also another 2 reviews. So hopefully will appear soon and on materials, right? So then I'm going to think a little bit late. I'm going to the second area of human-machine interface. For human-machine interface, just to use a couple of examples to show our visions, how we do the human-machine interface, right? So actually, we already gave the example during the Hypertext interface by electrotactile, we can control and so feel the feedback. So by the human machine interface. Here is exactly the same idea, but we are not only focused on our hands. We want it to monitor on every part of the body. In that case, you can just control a humanoid robots, and so do the exactly like control and also feel the feedback, right? So we put the skin integrated sensors on different part of the body, which can send a command, so capture the motion information, send a command to the robots. And the robots also have sensors. These sensors can detect the tactile and other information, which can send back the feedback to the actuators mounted on the user's body. The reason we do that is typically the human machine interface is based on the visual feedback. People see something and then they do the determination. However, so when you touch something and you do the determination, right? So you do the decision, right? So that will be totally different. The reason is the action, right? So from the performance area and from the habitat region, the visual region, the path, the difference. That's a natural reaction. So our accent people that give us, right, the gift. And you can find, so with such enhancement of the feedback, not only the visual, but also the habitat, we can not only wirelessly control a robotic arm to do this, copy these different motions. And you can also feel when you control the robotic hand to touch something, you feel something in your hand, right? Also shown here. And it can be used in many areas, such as the work was done during the pandemic. We try to use this system to replace the current COVID sample collection robots, as well as we can see the possibility of such a human-machine interface to control robots for this nursing work. I think it's with the aging, so age population increase, that's a high demand for this area, okay? And so based on the touch, there's quite a lot of other things to do. Another work I would like to share based on human-machine interface and the human-machine-human interface, that is based on this touch IoT. We give a name is touch walkie-talkie, right? So we use the walkie-talkie talk with other people, but we can also transmit the tactile information not without saying anything to other people. It's also possible. Well, the challenge is that in such a small area, you also need to have sensors and actuators, how to make them together. And one idea came to mind is how about we use a sensor as both a sensor and actuator? That's the two-in-one device. And we use also the electromagnetic method. So when it's as a sensor, you can find, so when you press it, right, the copper coil will generate the induced current, and will read the induced current voltage. You can use the sensing signal. And when you input the electricity into the copper coil, the magnet will be also vibrating, right? It can be an actuator when you contact with the user's body. So it's a double way, right? As an actuator, and we tune the vibration frequency, so it can be resonant at around 200 hertz, give people very strong sensation with very low input power. And so people can use this one for this double way transmission of the tactile information. It can be used by transmission information between two users who cannot speak. And it can be also used by the training that one teacher send a command to the different student, right? So we also use the olfactory virtual reality as the human-machine interface, give the information beyond the tactile, beyond the visual, beyond the auditory. So since there's a group of people called deaf blind people, they cannot see, right? They cannot hear. So that's the only information they can receive is the touch and the smell. And we bring these odor generators, olfactory virtual reality, that can bring this smell associated with different messages communicated with other people, right? And so the next area, so I'm going to talk about the skin electronics, which is more focused on materials. The reason is, although there are quite a lot of people working on the wearable sensors, wearable devices, however, so let's just come back to the very, very scientific challenges. It's very hard to solve. Why is the accuracy issue? The other thing is the stability issue. How to solve that? Let me give you one example. Even not, we are not talking about the wearable devices, even our cell phones. So if you are continuously working on cell phone, doing the video conferences, and for a while, it feels very hot. And then, so the operation speed is very, very slow, right? You have the experience. The same for the wearable electronics. Another thing is the difference that when you use the wearable electronics with a high performance, devices, so when it's very hot, it can burn our skin. So we collaborated with our colleagues also from CDU Hong Kong, Professor Lei Dangyuan, to develop such a passive cooling technology, pure based on materials. We're not using any water, any fan, just based on these coating materials. Such materials are based on the combination of silicon dioxide and microsphere, and also titanium dioxide and nanoparticles of fluorescent pigments, and also these are polymers. On one hand, the solar will be reflected. On the other hand, the heat can be dissipated in the implant, and then based on the radiative cooling to emission to the outer space. Since in the outer space, we think the temperature is absolute zero. So everything on the Earth, the temperature is higher than the outer space. It can continuously do the emission of this temperature. And from this optical data, you can find the performance is very, very good. And the maximum temperature is cooling down is 56 degrees, right? For such a passive cooling materials. And it's just a thin film. And so we can also use this one, which is compatible with the manufacturing technology to make it as a stretchable formats and can improve the performance. Most important thing, so back to the challenge I just mentioned, when it's very hot, when there's a thermal or optical interferences on our sensors, can we still get these accurate and stable signals? And of course, no, right? But when we code such materials, you can find. So the answer is yes, right? You can get these very stable signals because it can lower the interferences, the noise, right? And cancel these noise, still got these feature peaks, right? Okay, let's back to this concept again, right? So for wearable electronics, so accuracy stability issue not only based on these thermal issue, so many things we need to solve, right? So many things. So when we use the wearable devices, we do the activity, and when we sweating, so what will happen? When we sweating, that is a device signal will be also deteriorated, right? So it's maybe due to the contact issue, or this may be due to these connectivity changes, the motion artifacts, a lot of things. And also collaborate with excellent scientist, Professor Xinge Yu from the Polytechnic University of Hong Kong. So we developed a series of air permeable electronics that gave us the opportunity to solve this challenge. Well, the work is started the collaboration between the two of our students, Guanming from my group and Qiuna from Zijian's group. And based on Zijian's well-established this spinning method, this mat, which is the porous air permeable with this patterned liquid metal with a high resolution on that, we can make electronic devices, everything on that, and which can be also used for the implantable purposes and also the bio-integrated features, right? And we have another work is accepted, not published. So hopefully, published very soon, and we can share the future works, and which is also based on this concept. And so still have some time. Let me talk about the last part, which is the biomedical application. So with the concept of the skin integrated, the skin electronics materials for the biomedical just started from some particular application. The first one is the cardiovascular disease you can find, which ranks number one of the deaths among all the diseases. So because the plaque is typically happening in the vessel, and no matter when it's broke or it's just block the vessel, it will cause very, very dangerous thing. And the data is very shocking. So 66% of the people died outside of the hospital. That highlights the importance of continuous monitoring of the cardiovascular disease. What is related to the cardiovascular diseases, such as the ECG, right? Our heart signal, the blood pressure, right? Blood pressure. So people may ask, okay, so we have the blood pressure monitor at home. sorry, that's not continuous, right? Without continuous data, it means nothing, right? You need to detect and not say so every second, but every 10 minutes, right? Or every 1 minute. So in this case, so we found that there are quite a lot of challenges doing this continuous high quality monitoring. So since quite a lot of people working on ECG, however, so many things. So it's a challenge, such as the bulky, right? Bulky things. People do a lot of so integration, so can solve this. However, the electrode, so contact with skin, the like a sweating, air permeable issue, as well as the allergy issue, will cause the uncomfortable and the signal not accurate. So how to solve that? Can we develop these thin, soft, wearable, and sweat air permeable devices? And we go back to the previous work we found. There's previous air permeable electronics are typically materials driven, so which cannot give us a very high performance electronics. And you sacrifice the performance electronics, and of course, we cannot meet the clinical standard. So we are thinking about whether we can realize either the good air permeable materials without changing the current structure and devices, the formats, the electronics. So we suggest that this 3D liquid diode concept to give the air permeable capability at the meantime to maintain the good performance of the device. Well, the 3D liquid diodes are based on different layers. The first layer is closed by the treatment of this layer, so the sweat can be absorbed and anti-gravity is transported from the bottom to the top. And on top, we use the silicone make the microfluidic channel with the super hydrophilic and with the coating treatment. Once the water it's a drop on the surface will be just so go to the edge of the device, and at the edge you find there are a lot of pores, right? A lot of pores, and we just evaporate it. And at the bottom, so we use the well-defined these stretchable dry electrode, so which can avoid these white pores overlapping with this electrode, can further increase the comfortability as well as the sensing accuracy. And based on the data from the sweating rate on the human body, so this device can be 4,000 faster than the sweating rate of the human's body, and which is good enough. And you can find, so we compare to the traditional silicone, you input water at the bottom. For the conventional silicone, it cannot so transmit water together, and then it's lose the contact. Well, for this device, so the water and can still going up and transmitted from the pores. And we do the investigation so of the where such a devices comparison based on the commercial ECG electrode and the PDMS and the vertical liquid diode and the 3D liquid diode. We can find our 3D liquid diode not only exhibit a very good water vapor transmission rate as well as the very comfortability. And especially, so our students wear such a 3D liquid diode electrode for 1 week, it still can give us a very, very stable and high quality ECG signals. And so it can, so this is the advantage of the 3D liquid diode. Most important thing is 3D liquid diode, so it's also silicone based. You can just so integrated the well-established electronic devices. So on it, we based on the magnetic coupling, right? Stick on that, so which is quite stretchable, and it can Bluetooth transmit it, so the data to the cell phone continuously give you the high quality signal. And so the students wear such a device that do the 1 week test, so it's without any discomfortable, and also the sensing signal is very good. We also compare such a device with a commercial available ECG. We can find this is the data without further treatment. And so the ECG is the data you cannot read when you use continuous walking. And when you're jumping due to the motion artifacts, so the contact issue cannot read at all. Well, for our device can still give you the high quality feature peak. And here is the treated data you can find. So after 5 minutes cycling, so our device can still give us the very stable output of the signal. And even 20 or 30 minutes after the bicycling, you can see commercial one cannot read, but our device is good enough. Most important thing is after 30 minutes cycling, so the signal is good at the beginning, right? But the commercial one is not good at all, right? We can also use this one to integrate with the clothes to realize these wearable devices for this multiple purpose of the application, right? For the clothing, I think it's also possible, right? Back to the cardiovascular diseases, we mentioned the ECG, right? Another thing is the continuous blood pressure monitoring. If you want to realize the continuous blood pressure monitoring, so there's a couple methods we can use, such as a bioimpedance, ultrasound, optical pressure. Each of them has their limitation. So due to time limitation, so I cannot go further. So the conclusion is I still prefer to use a very traditional mechanical method based on the pressure strain sensing. And we suggest the combination of the materials and the algorithm and the mechanical design of such device to realize continuous blood pressure monitoring, which is based on the PWV, pulse wave velocity. We have two sensors on top of the arteries and the blood. So it goes from this region. You have two peaks, and also you have a time delay. And so the innovation of this work is we created a very stable contact interface because we use the traditional PZT so sensors with the airbag as a back to continuously pressing the PZT contact with the skin very well. And if any bad signal detected by this system, so the airbag will pump by itself. You can see, so the device always give us a very, very good sensing signal. No matter if you bend your auto west from 0 angle to 45 angle, right? And all very dynamic change. We can always get this good signal. But without this back pressure, so the signal cannot be read at all, right? And combined with algorithm, so the device can give us very, very high accuracy of the sensing signal, which is the most accurate device, right? So to date, and all falling into the grade A level. And so collaborating with the 301 hospital, we collected 87 people's data you can find. So it's the all in this region, right? All in this region. Okay, so I need to speed up. It's almost time. And so the wearable electronics, so I also want to share is the pathogen detection is also possible. During pandemic, we were thinking whether we can use a device, just a blue one time, and it can tell you whether there's a coronavirus or not. And we use this antigen and antibody bonding method, and we found it works. And but it take a long time, right? But finally, we make it. So here you can see is the results. That's people with a positive and negative cases put the device in the glove. When they pass this gate and wirelessly data can transmit it and to read this signal, can tell people, then it can be used in many, many areas, right? And of course, based on the microfluidic biosensor design, AI algorithm, so I cannot go through, right? So another thing is the pathogen or virus also exists widely in the dream, right? You can see it's everywhere. Especially the pandemic happened, how to detect the virus in underground, in the dream. So that's a big problem. So our idea is whether we can develop such a small robot can go to this confined region to wirelessly activate it and then to read this signal. And we use this wirelessly activated method based on the electromagnetic coupling that can make the device and go from one place to the other one, totally wireless. And in this pathogen-rich area, so when we use our cell phone to read it again, and you can find all this information can be read it, right? Can be read it. So the question is how we realize that. Here's a design of such system. So based on robots and carry a couple sensors and wirelessly power transmission modules on it. The first thing is how we design a fast swimming robot, also based on the resonance. And Professor Zhao Qianxie from Dalian University Technology provided very, very good support for this mechanical stimulation. And we can find that based on the stimulation, so our robots can swim very fast, right? Another thing is the high efficient power transmission, and which can give us the devices so working efficiency, and also integration with the biosensors, and which can detect these signal from the ammonium as well as the cholera and coronavirus and other things, right? And then, so interfaced with our cell phone based on the NFC technology, we can wirelessly read it by our cell phone, other terminals that can realize this function. Okay, so I think it's just 1 hour, so consider a very good time. As a summary, so our group are basically working on sensors and integrated electronics, which is for system level application for the purpose of these 4 areas I mentioned. But in the future, I feel this big area of the soft electronics, biomedical engineering, so no matter from materials and manufacturing, and also the application can driven this area into another level. So that's hope more people can jump into this region, right? And at last, I would like to thank all my collaborators, and they provide us so different kind of great support. So it's collaboration and also the funding body. So sorry, there's no room for the slides. So such as the Research Grant Council and also Innovation, so ITC and so NSFC, so many others. And most important thing is I need to thank all my group members. So without them, so there's no such these works. And at last, thank the audience again for their attention. Okay, thank you.
Thank you very much, Xinge. That's amazing work, very impressive. I'm sure our panel have a lot of panelists will have a lot of questions to ask. But before we go to our panel, at first, what we'll do is actually first, let me just share my screen. What we'll do is actually have a first special session in celebration the 4th anniversary of iCANX Talks. So now let me invite our founder of iCANX Talks, Professor Alice Zhang, to do this special presentation. Alice, please.
Okay, thank you very much, Len. Yeah, I'm still excited, into Xinge's talk. So, yeah, let me, before go to the discussions, let me first share this, 4 years anniversary. I think, so exciting, and for Xinge's talk give me a lot of memories. And the very beginning, we really have, done something, and we have so many things to share. So for this 4 years anniversary, it is not easy. So I have a title for this just coming out. It's a long journey and exciting, discovery. So yeah, really a lot of things can tell. But the story go back to this, why iCANX come out is because and COVID-19 just come in, and 2020, the spring normally should be a very lovely spring with so many interesting things, exciting things like today we have. But that time, we really get at a very dark screen, so raining, versus everywhere, and a lot of uncertainty. So that time everyone blocked at home, so have nothing to do. But someone was here thinking, what we can do, what we can fight. So it suddenly came to me, worse is X. So I'm thinking that time we facing a X, because this X is not just a question waiting for us to answer, without it, science could not sprout. X is still the unknown field, need our discoveries. Without it, the society could not advance. X still is a magic link, for among our human beings. Without it, emotion cannot resonate. So exactly this was a feeling that time. I think, we met this, the people was thinking, we don't know what the versus is. We don't know what time it can be ended, but we need to something to solve it. So we start this iCANX. So we believe that each cell on this earth is a small universe. We believe that communication building bridges among our small universe. We believe that numberless, small universes go together well coverage of boundless universe, changing a present, creating the future, leading our human society into a new era. iCANX, connect world and universe. This was the first day I read down all this, both in Chinese and in English. But this is exactly the feeling that time I'm on, because I'm thinking, though I was broken, all of us broken in a small can.
Alice,
Hi.
do you mind moving to slideshow? We can only see your first slide.
You
Go
can
to
see my,
slideshow. We only see your
That-
first slide.
did you see that? This was the work?
Yeah, go to
Hi, Mark.
slideshow.
This one? Can you see this?
Yeah, we can, but do you mind
It's
moving?
not a slideshow, yeah.
It's no slideshow. We are seeing your outline.
Oh, God. Yeah,
You have
I got
multiple
some,
screens and we are only seeing your slides.
I
we're
got
not,
some trouble with my sharing. Okay. Let me stop share this. Oh dear. I already stopped. You see that? Stopped, right?
yeah, stop now.
Yeah, let me share it again. I think I might have some problem. Okay, got it. Oh. Uh-oh, sorry. Sorry for that. I make, a fun PPT. Okay,
Yeah, we can see it. It's just not in the animation mode.
And it's not moving.
Yeah, it doesn't move. So just go to the slideshow.
It's this one. No, sorry, I did. Let's see. I mean, maybe it's my network, something wrong.
No, you have multiple screens and the one we are seeing is just your
You see the
slide
right
panel.
one? Martin, you see the right one?
Let's see, it's
Coming up
coming.
here. Yep.
You got it?
We're still seeing the outline, not the slideshow.
Okay, I think it's my computer get something wrong. Oh God, sorry for that. Hi, 小川 can you share that? 导播，你可以播放我的 PPT 吗？Okay, no. What's wrong with that? Okay. Oh, okay. Wrong one. Sorry. Yeah, stop share that one.
Okay.
No, Martin, it's not that one. Just finish this, okay? Yeah. 导播，你现在下载一下我的那个 PPT. You share that? Okay, sorry. Uh-oh.
Okay, Alice, keep going. I think what we need to do for those of us who are in the virtual room, just pin the iCANX talk living. That's where the slideshow is showing up. Alice, you can keep going.
No problem. It was, yeah, but he didn't use the right version, Yeah. How about to use that one? Sorry. Yeah. Okay. 导播，你可以播放我刚发给你的 PPT 吗？回到头一页，不对的，我刚才在微信里发给你一个新的，有吗？
Yep, on the iCANX talks, the live one is showing the right PPT. So I think it's just those of us who are in the virtual conference room. If you can go there.
Okay, yeah, we move on
keep
this,
going.
but
Yep.
Okay, yeah, okay. 导播你就用这个 ，OK， 好。Hello everyone. So excited, but made something wrong. Sometimes you prepare too well. That means you got some troubles. Yeah. So yeah, actually today was such a big day. So I'm really excited for share the stories with all of you for the iCANX. From very beginning. I think it's spring day, but it's block everyone. So that time we're thinking what we can do to get everyone connected together. So we think about to use this iCANX talks, get everyone can uniform online. So we got this talks started, and we got the words is connect world and the universe. Next page, please. Okay. Yeah. So that we start, and 2020, So April 17th. April 17th is an amazing day. It's a Friday. So that day we have the speakers, from a different part of the world. We have the number one speaker was John Rogers. And the first week, the four speakers on the stage, John Rogers and, Tony Huang. Next page, please. Okay. Yeah. So we have Rogers, Tony Huang, we have Xinge, and me was a moderator, Xinge was a panelist. So Rogers was the number one, talks, and Tony was the second speaker. So we have two speakers that day and Friday. So show next page, please. Yeah. So Rogers got my first certification is number one speaker on iCANX. So Xinge, you must be proud of that. It's a supervisor. Yeah. So it's so exciting. Rogers got the exciting talk and really inspiring everyone. I think it started a fire. So yeah, we have about 8,000 people on the stage to listen to his talk. So exciting. So yeah, the talks then keep on going, and we have more speakers. Next page, please. Yeah, we have many people to get on this involved, and we have a lot of people. Please next page. Okay. Yeah. Yeah. You see that we have the people get online, so exciting. So yeah, the talk is really, starting the whole world and, get us into a virtual, science talk online. So that time everyone was so exciting. So we hosted a lot of people here. Okay, please move on to next page. Okay, yeah, so in the last 2 or 3, 4 years, we have hosted more than 1,000 scientists here. And everyone sees this page, it will be so exciting, so many familiar, famous professors, scientists get on the stage. Okay, next page, please. Yeah. So Xinge said, not his first time on the stage. See, Xinge, what time you on the stage? Remember that? Yeah, 2020, December 11th. So you are on the stage. By that time, look at the title. Was a Mind Young Scientist. Yeah, so that time you win the title was Mind Young Scientist. So we have the young scientists here, together to deliver the talk. But we not only have you, we also have a next one. Next page, please. See who is on the next, slides. So Martin. Martin that time was, wins the title was ACS Nano Rising Stars. So yeah, iCANX, always we have the top scientist, senior, most famous one. So we really, want to have this outstanding young scientist. So we have that as special sessions. So Martin was there as ACS Nano Rising Stars. So Xinge there was for the Mind Young Scientist, awards. So yeah, but we think this is not fierce. We need to have more and more young scientists showed up. Then we have our youth talks. So next page. Yeah, we have our youth talks. We have a lot of people to come on. So this was our, panel. Yeah, we have a full line. We have different people from all over the world to host the sessions. To deliver the talks. And we have the, set up iCANX associations. We also set a club, here. And so next page, please. Yeah. So see, we have, not only talks, we have awards, we have a hub to hold everyone. We also will have a summit for meet the people in person. We have some service. We also have a fund to sponsor our scientists, for startups. So that's like an ecosystem we're setting on. But we want to host more, people here. We want to especially host more young scientists here. So yeah, next page, please. That's we have, our young scientists get on the stage since 2024. So this year we continue for young scientists, talks and youth talks and Tuesday we have the Friday, for iCANX talk, that's we're here. So every week we have twice. What's the future for this iCANX? That's a past, few years we did. Next, we're going to invite, our co-chair, Martin. Yeah, next page, please. Yeah, we're going to invite Martin to introduce our future. So Martin, it's your time. Okay, please share your slides. Yeah.
All right. Thank you, Alice, for the exciting overview. It's amazing that it's been already 4 years since we started this series, and I'm so glad to see a picture when I was a little bit younger. So now I want to speak about the future. We are all meeting in iCANX in Davos for the 2024 summit. It's a beautiful place in Switzerland, and it's going to be from July 11 to July 12. And the theme of this summit is innovation, science, technology, investment, management, and entrepreneurship. We are looking at the completeness, the holistic view of science innovation. And that's why we are the abbreviation is time. It's time for the science to move beyond good science into technologies and into businesses that will help people translate that science. In the summit, we have invited world leaders in all aspects of science, from very well prominent scientists, non-scientists, to people who are in industry and management. The summit is going to cover 107 countries, about 1,200 top scientists, and we expect to reach about 275 million people. And this is the committee we have for this. Everybody from iCANX is going to be there, from the organizers to young and old, from the founder all the way to the current team. For our panel lectures, we have Nobel laureates, we have presidents of academies and universities, top figures in science and technology around the world. Just to highlight a few, we're excited to have Jean-Marie to join us. Of course, our friend Jagadish Chenupati from Australia Academy of Science is going to be joining us. People like, of course, John Lodges, speaker number 1, is going to be there. We have Joseph De Simeon, a very well-known industrial and entrepreneur, is going to be there. Maurice Steven, Ali is going to be there. So we have a lot of people. Ruping Zhao is going to be there. So please come and join us and come join this wonderful, wonderful team of plenary speakers that we have. The highlights for the forum, of course, Jean Malnain and Landy Sheckman are going to be there from France and the US. We have presidents of University Forum. We have president of Bad University, Sun Yat-sen University, Hong Kong University, City University of Hong Kong, and we have KOC University. All of them are going to be spearheading that. From the president of Academy Forums, we have Peter Sayes from Swiss Academy of Engineering Science, and then, of course, our friend Jagadish is going to be there from Australian Academy of Science, and we're going to have Dubois from the Swiss Academy of Engineering and Science in Switzerland. We are going to have parallel sessions from investment and entrepreneurship, management and economics, nanotechnology, physics, chemistry, neuroscience, bio and biomedical engineering, computer science, advanced manufacturing. All the fields that you see on iCANX are going to be represented. So please come and join us. We have an exciting schedule running in parallel. And of course, we're going to have the young scientists, our Ds, who are going to be there. They're going to have, we're going to have a separate session for them. Come and see the future of science from these global leaders, as Alice has already highlighted from the last 4 years. There's going to be awards. We will be looking at promoting future innovative scientists and entrepreneurs. And these awards are encouragement. We want to encourage people who are innovative. We want to encourage our young scientists. We want to encourage startups. We want to encourage a completeness of the ecosystem. You innovate, whether you're young, whether you are more established, come together, look at how you can take your science to the next level. And we want everybody who is involved in that enterprise to be involved. And those awards are going to be given there. We're going to have our own science Oscar, so to speak. This is more than a summit because we have an exciting program. We have an exciting venue. To remind everybody, Davos is where the G7 goes to meet. So if the G7 global leaders go to meet there, why can't we also do the same thing as far as science is concerned? So come and see what we're going to have. Besides the lectures and exhibitions, we're going to have a lot of entertainment. And we are trying to make this a very friendly, very integrated summit for everybody. So we want to invite you for the gala dinner, and where we look at the human innovation and celebrate human innovation during that dinner. We're also going to have some entertainment. Some of it is we're going to have a jazz party, and we will basically be completely engaged both in the serious side of science and also in the entertainment. So please come join us in iCANX Davos, and this is the beginning of another chapter. And I hope that we will be celebrating these summits maybe 5-10 years to come, Alice, and we can talk about the kind of numbers that we are seeing from iCANX. And with that, I want to say thank you.
Thank you very much, Martin. That's really exciting and looking forward to it. And everyone, please come and join us in July. So now let's back to our talk. I hope you still remember your question. Let me first introduce our panelist tonight. So our first panelist tonight is Dr. Ruijie Sun from Southampton University. Dr. Ruijie Sun is currently a lecturer, assistant professor of soft electronics and multi-scale medical robotics in digital health and biomedical engineering group within the School of Electronics and Computer Science at the University of Southampton. Dr. Sun received his PhD at Bristol Composite Institute, University of Bristol in 2019, and his research interests include flexible electronics, medical robotics, 3D printing, and intelligent metamaterials. Our next panelist is Dr. Yu Song, who is from California Institute of Technology. He's currently a postdoc scholar at Professor Wei Gao's group at CIT, and he's an incoming presidential assistant professor at the Department of Biomedical Engineering at City University of Hong Kong. Dr. Song received his PhD in microelectronics and solid-state electronics at Peking University under the supervision of Professor Alice Zhang, and his research interest focused on bioelectronics, wearable sensors, advanced manufacturing, and digital medicine to achieve wearable bioelectronics for personalized healthcare. He has published 70 publications, many in very top journals, and he has won a lot of awards. Our next panelist is Dr. Xinge Yu from Yonsei University. He's an associate professor at the School of Electrical and Electronic Engineering at Yonsei University. And Dr. Yu also, he obtained his bachelor, master's, and PhD degrees in electrical and computer engineering from the University of Illinois at Urbana-Champaign. And also he did his postdoc training, they all under the guidance of Professor John Rogers. And he also did his postdoc training with Professor John Rogers. His research primarily focuses on developing soft electronics biomedical applications. He has also received lots of awards, including outstanding achievement in both research and teaching for many years, continuous years in Yonsei University. Our ex-challenger tonight is Yaozhen Wang, who is from Peking University. He's currently a PhD student in the School of Integrated Circuits in Peking University. He received his bachelor degree from the Northwestern Polytechnical University in 2022. His research interest includes wearable electronics and sensitive materials in MEMS. So now let me inviting all the panelists to the stage. Okay, so as always, we start our question from our ex-challenger. So go ahead, Yaojun. Do you have any questions to our speaker tonight?
Yes, thank you, Professor Fu, and thanks for Professor Yu's excellent lecture. After listening, I have two questions. The first is about the encapsulation. I see some of your work encapsulated by the soft materials such as silicon and elastomer. So my question is, how about the consistency after encapsulation of that array?
Okay, so what do you mean the consistency? So the performance. So after encapsulation, always a bench to from bench to bench.
Yes, the performance of the different devices.
Okay.
After encapsulation.
Okay, so the encapsulation sometimes is the outside layer is the PDMS silicon. Well, so typically, so there is the polyimide to encapsulate the interconnect circuits. And there's also like a parallel or something. And so we also have some interfacial layer as the bonding layer, so between the electronics and the silicon. So I think so we didn't find the consistent issue. So as long as the device is working, so it's so another thing. So since we are not working on the novel materials, so most of our works you can find. So a lot of materials that we purchased, so commercially available. So the performance is very stable. So from bench to bench. So even after encapsulation, so the performance is still stable. Yeah. Thank you for the question.
Okay, I know that. And my second question is about your work on that cool and disruptive technology of skin integrated virtual reality systems. And I want to know how to combine the wearable devices with an application appropriately, such for example, like your virtual reality systems.
So if I understand it correctly, so are you asking so beyond the virtual reality, what other opportunities do you think so by combining the wearable electronics, right?
Yes, just to combine the devices with some applications like your virtual reality.
Oh, okay. So what's the application of the virtual reality? So wearable virtual reality, okay? Yeah, so this is a good question. So I think so there are a couple of applications. The first one is the entertainment. So as I mentioned in the metaverse, so no matter it's the gaming or the social media, so bringing another dimension of the sensation. So I mean beyond the visual and auditory, so that's touch, right? So that's will be means a lot for this application. So beyond these social media and entertainment, so the training is also very important, especially the VR training. So for VR training, so people typically can see these things and they use the motion tracker, typically the visual based, and track their hands to grab something and do this type of training. Well, they cannot feel. So in this case, the lack of this real sensation. If you can bring the touch sensation to the training, it can also make the users more so adapted to these so critical right application. So training can be from the industry training and the medical training, and such as the manipulate the so the medical robots, surgical robots, and also these type of training. So another thing I think is for the biomedical, such as the prosthetic sensing and control. So you already found, so we showed here. So there are quite a big demand. So in this area, so even there are a lot of companies produce these prostheses. However, so they typically use the EMG signal to control the grabbing of the robotic hands, and the user cannot feel this feedback. So even though they feel like a thing, once they can feel there's like a strong or weak feedback can associate with the weight or this grabbing force, interaction force, that can give the user more precise feeling, and then more so it's better to control the prosthesis, right? So that's a couple applications, but I think it's more than that. Yeah, thank you.
Okay, thank you. That's all.
Now I think the panelists feel free to jump in and ask questions.
I can start if it's okay.
Please go ahead. Yep.
Yeah, thank you for Xinge's wonderful talk, and also congratulations for the fourth anniversary of the iCANX talks. It's always it's always exciting to see that the technology is coming from the lab to the real life, and the Xinge's speech is always inspiring every time, and the work is very innovative. And I have two questions. The first one is for the abdominal VR, and it's very enjoyable to see that many applications from the VR applications for the immerse tactile sensations. And Xinge's work has demonstrated that the entertainment application is very useful, I think. But apart from the for the game entertainment applications, the biomedical application, which is following the previous question, can you imagine that whether this haptic interface can be applied for the surgical robot? We know that in the surgical robot, the machine is replacing the surgeon's hand. So the machine will lose the tactile information. So whether this technology can be applied in that area, and what kind of like challenges it might have.
Okay. Yeah, Rujia, thank you for the question. So definitely, so the Habitat interface. So I would say it's the Habitat interface rather than the so the touch VR. So definitely, it's very, very important for surgical robots. That's also something we are collaborating with hospitals doing that. So I think there are quite a lot of challenges by combining the Habitat with the robots. The challenge number one is the sensor, right? So now all these surgical robots are already so well defined. So there's a very few room to put the sensors on. Well, I think one possible strategy is to use the video capture, right? There's a camera to see. So they already have quite a lot of algorithm to see this color change, right? So there's a contrast difference, and to use this one to do the estimation of the force. And then we can use this information assign the force to the underuse, which is very important. So not only the surgical robots, but also the underscope, so operation procedure. So people cannot feel the very strong sensation, feeling sensation. Well, so that's the reason only very experienced doctors or physicians can operate these. So in this case, with the Habitat interface, it can significantly, shorten the time of experienced, like a less experienced surgeon to operate the surgical robots. But the challenge is how to connect the sensing and the feedback projection. So I think that's some other things. I feel there should be much, much more good idea to solve these challenges. Will the Habitat itself, no problem. So the sensor itself, no problem. How to put the sensor on the robots and project the sensing signal to the Habitat, that's a challenge, right? Because not a lot of people working on this area. Yeah, thank you.
Thank you very much for the answers, which is very clarifying my questions. And the second one is, so in the latest Nature paper, you mentioned the permeable electronics, and I think it's very potential to achieve the real-time monitor of the health of the human body. And I'm wondering whether this kind of like technology can be applied into your previous work of the abdominal VR. So in your previous work, it is a whole batch, and it's based on the silicon. And I think the sweat or the air permeability is also an issue. So whether it can like combine your latest like technology.
Thank you, Rujie. So I think so you probably, so give our students another couple of papers, right? they have ideas, so combine our previous work with this new technology. Yeah, so definitely, I think so. So no matter what type of wearable electronics, so as long as for the like a sensing application, whatever, all suffering from the long-term stability issue. Since when we wear on these, so even the sweat sensor, right? You still have sweat, and you don't want the unwanted sweat, only so the collected sweat in the desired region. And also for all the wearable devices, so we need to avoid these things to improve the sensing accuracy. It's definitely so it's worth to try. And we have some initial idea to combine, but I think it is quite so quite a lot of things can combine. So I think so this is a good so research areas and direction to try to solve these different particular regions areas based on these combined technology. Maybe not only our work, but also other people's work, and based on this air permeable technique. Right. Thank you.
Thank you.
We have a question from Dr. Xinge Yu, because he's in the public area, cannot talk. So he typed in the chat asking a question for everyone working on soft electronics, which is about the challenging for wearable and implantable devices, that how can we improve the reliability and the durability compared to conventional electronics?
Yeah, so this is a very challenging question. I think so Kijun should know this better than me, since Kijun is really an expert in the implantable electronics. He has been working on, so I think this is many years since we were at Rudder's group. He's the #1 expert in this one. So definitely encapsulation, right? Encapsulation is one like strategy. So another thing, so I'm always thinking it's just so discussion. Maybe I'm wrong. So encapsulation materials, especially use this like a silicon dioxide, the back etching method. So Professor Rogers gave the idea. So it's very useful. So however, it's a huge hero engineering right work. So how about use the modification of the materials to make it hydrophobic, hydrophilic, or use some electricity can control this surface, and which can maintain a certain period, can make the device in a stable state. Since for the implantable, we don't expect it's working on a long time. So especially for from the materials at the state of art materials. But in the future, so definitely. Well, in the future, definitely for other applications as encapsulation, we may need to sacrifice some flexibility, use the conventional encapsulation methods or materials to encapsulate these so less importance areas, such as the circuits and battery, and only put our sensors, right? So it's can be replaceable, right? Can working on a certain time. So rather than so it's computed to the conventional electronics can implanted there and working forever, right? Okay, that's my thoughts, right? Thank you.
Thank you. So any other questions?
Yeah, so actually I also have 2 questions. So first, thanks Xinge for a very nice talk. Yeah, actually I'm also glad to be here again, because actually I was the volunteer for the first iCANX talks 4 years ago. At that time I was still a PhD student. Yeah, I have 2 questions. So first, still the recent the paper published in Nature for the permeable electrodes. So actually I'm a bit curious, like it's still like is it a one-time work electrode, or it can be used even after several times, like attachment detachment from your skin? And also, could it be used also in some other environment, like the implantable or some organs? Because for example, the heart actually also has some pericardial fluids, so it might also have some problem. We want get some ECG signal or other signal from some implantable environment. So is it possible to use this permeable electrode in some other scenarios?
Yeah, thank you for the question, Yu. So the device is a multiple use, so it's not one-time use. So
okay.
But we need to use like glue, so it's a kind of bioadhesive layer, right? And so the materials themselves are already well established, like the clothes and the microfluidic. As long as the device can mount on the body, so with a strong adhesion. But so once we peeled off, so you lost this adhesion, and so next time you need to spray off like an adhesive layer again, right? And on top. And so what we do typically now is after we use, and so we put the glue on and use some plastic to cover it. And the next time you use it, you peel it off. And for your next question is whether it can use on organ. So I think it's the answer is yes. Well, so but the point is even though it's a thin, but it still has around the 1 millimeter or something the thickness. It may not able to maintain the conformal formats. Well, for the interface with organ, I would rather to use the other like the intrinsically air permeable electronics that's I introduced so today. But another work is accept I didn't talk about it. So let's also collaborate with Xinge. So they developed these like a fabric material, so with the porous, and so they use a very clever, so smart idea to pattern these liquid metal on the porous electrode. And on one hand, it can give you very good air permeability. On the other hand, it can also so achieve the high integration level of the interconnect and the circuits. And we also developed some method to combine with the chips, every electronic components with these liquid metal. But so it's may not able to compete with the conventional so electronics multiple layers. But for implantable applications, I think this is the so enough. Yeah, it can provide us so quite a lot of functions. Thank you.
Yeah, yes, thanks for the answer. So also another question related to the pulse wave for the blood pressure estimation. So does the like for example the location or the position also matter, especially there are also some might have some variation from person to person. So also for your machine learning data set, so what's a typical number of your group for you to get very high accuracy to predict the blood pressure?
Okay, so thank you for the question. Well, for the pulse wave, so that's true. So we typically put it on the west, and so most people is there. And so when we use the device, since it's our device is already encapsulated in a band, so when we use the device, we need to so it's manually adjust the device, and when we so got some signal. Well, the point is our sensor is not that small. So the sensor is kind of also big sensor. Well, they use the big sensor. The advantage is you got a large coverage area, and so the disadvantage, so this interfacial properties may not contact with other very well, and that's the reason we use the airbag at the back of the sensor. And when there's a gap between the sensor and your skin, and we pump the air back to push the sensor to contact with the skin. So in this case, it's not a big issue. So even you like a mispositioning the sensor a little bit, it can always work, right? It doesn't matter, right? And for the question why they combine with the machine learning how many groups? Well, these are sensors currently we still need to do the training first, right? Training first to do the calculation with the clinical standard continuous monitoring, all these cough-based. And so 1 people is enough. So you use the 1 people to collect like a continuous 5 minutes data. And so you use your device and do the training. So that's can be good enough. Well, the more people training, so is result is better, right? But typically, it's 1 people after training is good enough for this person to use, right? Okay, thank you.
Yeah, thank you.
Very good.
Right. I can jump in.
I guess you're keen to ask.
Yes, I can jump in because there are a few things that Xinge Yu said that are very interesting to me. First, very nice talk. Great work as always. And I want to ask a kind of an out of this world kind of question. Based on the development on both olfactory and haptic sensing. Have you thought about sending your system to space? So that when the robot is working on something like Mars or the moon, they can transfer those signals back to us, and then we can actually have an experience on the ground from the recorded signal. Because if you attach it to something like a Mars rover or a moon lander, it can feel the regolith and all the rocks in Mars, and then I can go to a place, pay, and then wear the thing, and I can feel like I'm squeezing the material from a different world. Is that even possible?
Okay, Martin, thank you very much for the question. So it's a very, very nice question. So I think so this when I answer your question, I think so Professor Alice Zhang may also have another candidate for iCANX. So we actually we had a colleague at the Professor Rogers group. He was graduated from Caltech, and his major is aerospace. And at the time we did a postdoc at the Rogers Group. He mentioned to me, so my future is to combine the wearable devices with aerospace. I want to use these devices as aerospace in a harsh environment. It's very cold, right? It's very cold, so it's may and the vacuum in vacuum level. So the environment is completely different from the atmosphere. And so you need to develop these materials, and if you silicon is the best materials, definitely, so no doubt. And so in this case, so for us, since we are not experts in the aerospace, but I'm pretty sure it's possible. So they already published some paper, but since aerospace is kind of also another so quite like a large distance from the materials community, right? So may not a lot of people read their paper before, right? So, but I think it is a very, very nice idea. So it's you are the second people, right? So that's give this a question. The first one is the expert in aerospace, and you are the second one. It's a very, very nice question. So I feel it is possible. And so this professor name is Xinge. Now it's in the PSU. Yeah, thank you.
Okay, I definitely will invite him. Okay, yeah. So, Xinge, we discussed this before. Of course, you wonderful work. You really in this new field draw a lot of attentions. But the thing is, years ago, I have discussed with you online. I really stress for all this AI stuff come out will replace me, right? I'm thinking is that possible to use this, as one part of my, input. Yeah. So not just a part, for the robots. It's one part of my input, help me to make the final decision. So yeah, I'm thinking, yeah, we need to work on this direction, Yeah. So you don't need to answer these questions, but I just, stick with my ideas with this. I think, we couldn't be replaced, Yeah, we have to be enhanced, not be replaced, right? So my other question for you is, Xinge, we use silicon materials, we use organic materials, we use all these kind of materials. But eventually, you want to, mount with a body or something, you need to use biomaterials. Right? You need to move to all these biomaterials. So you are in bioengineering. So did you have a work with someone for this real kind of biomaterials for all these things?
Yeah, thank you, Professor Zhang, for the question. Well, for the first so AI question, I think it's also important to bring this question to the like a panelist, also the audience. So everyone of us need to think about how to better use the AI, not be controlled by AI. So to make the right decision, right, by us rather than put the task to the AI. Right, I totally agree with that. Well, for your second question is the biomaterials. This is a very, very nice question. And so I think it's maybe also the future research direction for the biomedical engineering, not rather than the wearable devices, flexible electronics. Well, so since the human already is made by the carbon, organic based, so if these materials are very close to the human tissue with the similar functions, that will be great. But the point is, so even though I'm working on kind of so a little bit materials, but I'm not a material scientist. I feel it's a really need to really explore and do collaboration with the collaborators. So I'm always open and very happy to collaborate with other people, as you already seen from my slides. So a lot of works are collaboration, right? So for collaboration, I feel is a kind of we are doing research, like driving a boat, driving ships on the ocean, So it's so many, right? So it's a large area, so you need to drive the right direction. And here's something we need to talk about the ships, right? So many ships. The first thing is the collaboration. We need to have professional ship, right? Professional ship. That's so everyone use their own expertise to combine together, right? So this may be not small ship; it's a big ship, right? Another thing I think is like a friendship. So the collaboration, the collaborators once so doing the collaboration, right? So they need to have the same working pace and so many successful collaborators, right? So that's a good example. And also, so this co-authorship, right? Co-authorship, definitely, we have research output. At the last, it's maybe, so it's beyond that. So there's one paper I mentioned that's collaborated with Xinge. And so you see there are two authors. One is Qiuna from Xinge group. The other coming from my group. Now they are couple, right? So there's a coupleship, right? So that's a future, right? So that's I think so. That's something. So I want to use this story to emphasize the importance of collaboration. So only collaboration can bring this all the possibilities to be true. Yeah. Thank you for the question.
Okay, great. I think so you will feel really good because we are jumping in be your new partner, right? Yeah, in the same department. That will be a big future for collaboration.
Yeah. Look forward to it. Thank you.
Sounds great. Any other questions? If not, I might take the opportunity to also ask the question I feel quite fascinated about is the smelling detection. So you were saying that I really missed like how you detect the smell. You say you release the gas when you do the sensing there. Is that how you do it? Can you just clarify?
Yeah, Professor Fu, thank you for the question. So we can also actuator. So we release the gas. So and there's also a sensor. Will the sensors only detect the amount of the gas, right? So how we do that, so we have the different flavor candles, right? So we burn the candles and to release these pleasant smell, help us to go to sleep. We use the same idea. So we blend the wax. That's the basic material for candle. And so that's the food, right? It's a food level of wax. Blend with the prefer. So different type of prefer. And we have a different type of small generators, small actuators. And how we release the smell is to heat it up, right? When you heat up the candle, the wax, the phase transition will allow the prefer to evaporate, and we can smell that. We make each of the wax into a small block, and then to fill in like a device, the small device. There is the well-defined thermal actuators based on the electric, so thin film electrode, and you just put AC, so electricity into this thin film, and the heat can be generated, and then so the wax can be kind of also approaching to melt and the smell released. And when you want to close down, so how we do that? We also have a mechanical actuator, and when you input the electricity, the mechanical actuator will lift the wax so away from the heat, and so it can cool down immediately. So you realize the fast open and close of the smell. And this is the first generation. And on the second and the third generation, we also have papers accepted and going ready to publish that and under review. That's we also have some like a miniaturized design, and also with the design not melting the wax. So with some concentrated these prefer, and so we open and close so small size holes, right? So we create a small pores and open and close that can also release smell. So there's quite a lot of different technology to realize that. But the concept is the release smell rather than to use it to sensors to detect them, right? We release them, not the sensor, right? Thank you.
So you can really experience it, basically.
That's right. That's right.
That's really interesting because we're always fascinating by, you know, some restaurant could just send the advertisement and also with the smell, so you know what is there. That's just, yeah, very interesting. When you integrate all these functions together, so many different sensors and things, they certainly will consume a lot of energy, right? So what is the level and energy that you actually envisage that those when your integration level become higher and higher? So do you see that will be an issue? Especially if you would also talk about that Meta, the gloves, they have to very inconvenient and needs a lot of energy. So how those kind of thing will come into the consideration when your function becomes more and more?
You mean the power consumption issue, right?
Yes, that's right. And also
Yeah,
the
that's
sort of usability issue will come because you have all these things start to, you also, one of the system you mentioned, you need 100 volts of driving power to do that.
Thank you for the question. Well, yeah, the power issue is very important. So the power now we're using, if wireless, typically we'll still use the battery, since there's not quite a lot of options for us. So, and if the power is very high, so we don't have a that high power devices, and so it's so probably it's 100 microwatts, right? Sorry, micro or milliwatts. So there's from like several microwatts to the most, I think the highest one is the 100 milliwatts, right? So that's around that range. So if it's like approaching watt level, so there's also option to connect with the wire, right? Well, so for power like consumption issue, this is true. So especially for the long term, so the use. So the one solution is we also integrated the recharge module. So there's a wirelessly coil and can use the charger. So we use to charge our cell phone, exactly the same one. We can charge that. And another thing is we also think to use some self-powered sensors and to detect these signals. You don't need to, generate, you don't need to input power, to just use the generated energy. So another thing, so today I didn't talk. So we also is struggling in this field. So we also developed the another concept called a sweat activated battery. So we try to develop a very low cost battery, so which is the primary battery, and when we mount on the body and when we're sweating, it can breathe the salt bridge and give electricity. But today I didn't talk that. That is all the efforts we tried to solve this power issue. But so I feel the most feasible way is the development of the high density with the wearable batteries, such as lithium ion, zinc based and something, and then we can integrate it with our system. Well, in this case, so I think the critical usability should be not a problem. Yeah, thank you.
Great, thank you very much for sharing this. Very nice insight of that.
Maybe I take this opportunity to ask the question, the last question. Okay.
Yes, go ahead.
So because today was the 4th anniversary, so when I go through that, your talks, Xinge and Martin, and the 2020 as a young scientist, I mean that time you're so young. Although you are really, good job and a young scientist, but now after 4 years, I mean, you totally getting to be the top scientist. So during the COVID-19, a lot of difficulties, right? Especially for many students couldn't go to the lab. So I mean, both of you, how you got through this, Xinge jump a big, Martin also jumped so, so high. So what happened in the last few years? Can you share with us? Martin, maybe you go first. Then
I can go first.
Take a rest.
So Iris, thank you very much. It's for me, it's always boils down to people. Like if you invest yourself in people, you will always do good science. I took my students and we agreed. We had lab protocols and we had a lot of challenges. And then with with the lockdown, we just decided, first and foremost, are you healthy? Are you good? And that philosophy has carried me through. Once you make people comfortable, once you make your students comfortable, they're extremely creative, right? The people have a lot of talent. And when you invest in them, when you care about them, when you worry about them and they know it, they will do great work. I refuse to be a boss. My students don't even use any titles when they address me. They call me Martin, because I want them to be a colleague. And I learned this from George Whiteside. He's a world prominent scientist, but when you're in George's group, he's your colleague, and he will make that very, very clear. When you have his first interview with him, when you join the group, he wants to understand who you are, what your goals are, and he will help you get there. So I was very, very privileged to have that opportunity, and I take that to my group now. And Alice, actually, during COVID, we published some amazing papers in fields.
Yes.
I found myself in biomedical engineering, like publishing stuff about printable electronics and stuff like this. And I'm like, that's not my field. I'm not in that space. But all that happened during COVID. Of course, I had people like Julia Chang, who has been on this channel, and Andrew, who have been here, Boyce Chang, people who understood that we are together, we are a team. And that has carried through to this day. My students, I always treat them as we are one team. And once they know that, then you don't even have to be driving them crazy. They will do the work, and all you have now. The challenge becomes when you have a group like that, you have to always be thinking about new ideas. Where is the next one? And then so your anxiety is I have to be ahead of my students, and it's fun. It's a lot of fun, and I also want to have fun. I don't want to be stressed. Yeah.
Party, exactly right. Okay, yeah. All family, yeah, everyone take care to the others and, helping each other. So Xinge, how about you? Yeah, you really make big difference.
Thank you, Professor Zhang. So I think this is also the great support from Professor Zhang and also all the colleagues and friends. Well, so I think so even now I'm still realize there's quite a lot of things I need to learn. So physically the reason, so during the pandemic, so that's Hong Kong, so kind of was isolated, right? So it's very close to mainland, but the border is closed, so the students and either students or me, so we can go nowhere, right? That's what the students have to stay the time at the lab. This is a physical reason. Another reason is I think so. So even now, I still learn how to be a good advisor. Well, so before I know, so the direction or the supervision direction that's fit me very well. So I just copy the working modes from my advisors. So I have 4 advisors, like Professor Xinge Yu from UESTC, and Professor Tobin Marks and Professor Antonio Facchetti from Northwestern, and Professor John Rogers. And so I learned a lot from them. So especially the working style of the Professor John Rogers, it's just a copy and paste. And I found it's very hard. It's really, really very hard. So this quite so difficult to manage. And so I also encourage my students. So when we do some research, especially we call this a high quality research, we try to solve some very critical issue. But the critical issue typically is very hard. So students, so I think advisors know the problem. Sometimes students, they may not know it very well, and they prefer to choose some work that can be published in a short time. So in this case, so I would, say encourage them, so now we are working on a great project, So this project, so the questions is now in front of us. So I don't know the answer. So if I know the answer, I can tell you this won't be a good paper, right? So that's the question both of us, we don't know. So, and we need to explore. And so based on my expertise, based on my knowledge, and based on efforts, and I feel this direction is right. Let's work on this direction. And the students are very good. So they listen, and then so we meet. So it's the routinely, and then so gradually make a progress in a step by step. And so based on the bottleneck and the challenge issue, it can be very small, but so it's try the different method to solve that. And once that, and I also learned a lot from this process, and so a lot from this process, also from the students. I think the students and we are growing together. Yeah, that's my feeling. Yeah.
If Alice, I can just add one more thought. One of the things as a young faculty and as a faculty is to always see yourself also as a student with your group and accept that there are things that you will know and there are things you will not know. So always find good collaborators. You may have a clue, you might be able to use something or get an idea from somewhere else. Find people who can do things that you cannot do and learn from them. So as you take care of your group, as I take care of my group, I also try to identify who are the good collaborators who can help us. And that is how we've been able to span so many fields, even as a small group. I don't have a very big group, but we have spread out so much because we have a ton of collaborators.
Yeah, this is really the words I want to say. You know, how we gone through all this hard time, the pandemic for the last 4 years, because of collaborations. You know, from the whole world, we got the people's support. You know, we're fighting for the same questions, you know, the big questions. So everyone putting the force together. So thank you all very much. Okay, Len, the last
thank you
news,
very much.
Yeah, is we have today another breakthrough. Is on WeChat we have more than 10,000 attendees. Yeah. So
oh wow, that's really we become very famous, Xinge. All right, so thank you so much. I think that's what we have the time for today. So let me now just go to my slides. So of course, again, thank you very much, Xinge, for your excellent talk. And this is the certificate from iCANX that Alice will send to you by email later tonight, as always. And next week, our speaker is Professor Yang Lu from the University of Hong Kong. He'll be talking about deep strain engineering of diamond. So stay tuned for next week. And again, please join us at iCANX Davos Summit in July. With that, thank you very much, everyone. I'll see you next time.
Okay.
Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, and entrepreneurship. Short for It's Time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have a Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, you know, scientists, investment management to go together to talk about, you know, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invited you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us, and it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
汽车电子化的迅猛发展正在掀起一场技术革新的浪潮。其万千期待于一身的电子元器件，必须以更高的技术水平和可靠性，为汽车电子化提供支持。多层陶瓷电容器、电感器、高可靠性元器件，太阳诱电挺身而出，肩负起推动未来科技进步的重任。电子元器件的发展与汽车、工业设备和网络时代的发展密切相关。为此，太阳诱电开始了充满激情的挑战。心怀梦想，无畏挫折，不懈奋斗，为用户、为未来高新技术领域倾力打造、倾情奉献优质的电子元器件。太阳诱电将吸引全世界的目光。
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 iCANX 达沃斯科学峰会。那今年是第一次 iCANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第一个是创新 innovation， 第二个是科学 science， 第三个是 technology 我们的技术，第四个是 investment 投资，第5个是 management 管理，第6个是 entrepreneurship 创业。所以它结合